Alright, here are your worksheets, class. One for you. One for you. One for you.
It's collated, fool.
I thought it was
collated
when I went to walk.
Wow. You look pretty good at this, Sam. I'm not surprised.
You're Mr. Park.
I don't know what you mean by collated.
You just grab the top of the thing.
Maybe it works. That's pretty cool. Oh, you're right.
Thank you, Mr. Park.
Stop laughing at me.
Put the rest of the papers there, Mr. Park. By the bear. And begin the lesson. On this 2/3 of the board.
Okay, class. So, does anyone here know about exponential and logarithmic functions?
No.
Well, I'll just teach you like you know nothing. Okay, so I don't know anything.
I don't have white on the back of my head.
Turn around, turn
Or
around.
do I?
Turn around. Oh, you know, yeah. A little bit. Wait, turn around. Oh, no, he doesn't.
It's kind of insulting.
Yeah.
Okay, so a log exponential is like this. And logarithmic is like the other stuff. I don't know.
Yeah, you don't know. Okay, I'll take it from you.
Thank you, Mr. Second Mr. Park.
Okay, today we start exponential and logarithmic functions. So first of all, what is an exponential function? Like the other Mr. Park said, it's a function of the form b to the x, where b is a constant greater than 0 but not equal to 1. So b gotta be greater than 0, but it can't be 1. How come it can't be 1?
If it was 1, then
Because it'll just be y equal 1, you just get a constant, right? Anyway, we know what exponential functions look like from last year, right? Let's pretend we don't know anything. Okay, like what does the graph of y, like if you don't know, plot some points, like 0. Plug in 0.
1.
1. 1.
2.
2. Negative 1. 1/2. 2.
4.
4.
Plug in negative 1. 2 to the negative 1 means 1 over 2. 2.
4.
4. Negative 2.
1, 4.
Okay, so it looks like this. That's an exponent. That's a typical exponential function. So when b is greater than 1, that's what it looks like. What if b is a fraction between 0 and 1?
Decay.
Yeah, then you would get exactly. So this is like exponential growth. And then if b is between 0 and 1, you get exponential decay. So it kind of looks like this. Come on, you've seen this last year. So pretty much every exponential function is going to pass through point 0, 1, right? Because any number to the 0 power is 1. And then if b is greater than 1, it goes like this. And if b is a fraction between 0 and 1, then you go. Either way, the x-axis is going to be a horizontal asymptote, right? Can you see why? I mean, not just from the graph, but
Yeah.
like what happens when you plug in a really small number for x, like negative million?
You a really small positive number.
Yeah, 2 to the negative million power means 1 over 2 to the million, which is almost 0. So that's why when the graph goes out to the left, it gets closer and closer to 0. Okay, so that's an exponential function. Now tonight's homework is all review. There's nothing new there. Okay, so let's look at some kind of problems you're going to see tonight. How do you solve an equation like this? 2 to the x times 8 to the 3x minus 1 is equal to 4 to the 5x minus 2.
Turn them into twos.
Yeah.
Yeah, this is the kind you get on the SAT, right? You make a common base. What's the common base for 2, 8, and 4?
2.
2. So you can write all of these using powers of 2, right? So 8 is the same thing as 2 to the third. 4 is the same thing as 2 to the second.
Wait, you put
I did it! Just roll the camera back. You'll see I didn't write it. 2 to the 2. And then you just use your rules for exponents. What do you do with the exponents when it's outside the parentheses? You multiply them, so that's going to be 9x minus 3, and this is going to be 10x minus 4. And then over here, you add the exponents, so that's 2 to the 10x minus 3 is equal to 2 to the, uh-oh! How did that happen? You'll find out. Okay, so if 2 to the gorilla equals 2 to the banana, doesn't it just make sense that gorilla gotta equal banana? But the 10x's cancel out, and what's left is an untrue statement, so there is no solution for this problem. I didn't want the x's to cancel out, but it did. But that's okay. Anyway, if the x's cancel out, that just means the answer is either going to be no solution or all real numbers, right?
Yeah.
So if all the variables canceled out and you were left with a true statement, then the answer is all real numbers. In this case, no solution. Okay, now let's kick it up a notch. You guys think you're good?
Yeah.
Okay, how about this? 3 to the x plus 3 to the negative x equals, shh, 10/3. How do you solve this equation? Anyway, you guys remember doing problems like this last year? No, see. No, we're not doing logarithms yet. Okay, see, like in this problem, see, all of them, you can make the same base. But if you cannot make them all the same base, that's when you're going to use logarithms. So when I give you, what if I give you a problem like this? 2 to the x plus 1 equals 3 to the x minus 1. See, you can't make the same base, so that's when you use logarithms. So several days from now, we'll be able to do a problem like that. Right now, we don't know how. Why, do you guys remember logarithms?
No.
Do we need a calculator?
Yes, you need a graphing calculator every time.
So,
Anyway, second semester, when we get our iPads, we don't even need your graphing calculator anymore. No, because you need it to take the AP exam next year. Because on the AP exam, you're not allowed to bring an iPad in or an iPhone. You only can use an approved graphing calculator. But we're going to get a program that on the iPad that makes the, yeah, you don't need the graphing calculator anymore. Anyway, how do you solve an equation like this? Well, for those of you who remember, this is going to lead to the quadratic equation.
Oh, you. Let's go somewhere over there. I forgot.
yeah.
Okay, this is like 3 to the x plus 1 over 3 to the x equals 10/3, right? Now, remember last year, what did we do at this step? We made a u substitution. I think last year you said u equal to 3 to the x. So this becomes u plus 1 over u equals 10/3. Now can you see it's going to lead to a quadratic equation?
Yeah.
Some of you don't see it yet. Okay, how do you simplify this equation? Multiply both sides by the least common denominator, which is 3u. So you're going to get 3u squared plus 3 equals 10u. Now do you see it's a quadratic equation? So make one side 0. 3u squared minus 10u plus 3 is equal to 0. And hopefully this is factorable. 3u, u, 3, 1, minus, minus. So u equals either 1/3 or 3. Box that, that's the answer. No, because we made a substitution. So 3 to the x is equal to 1/3 or 3. So now you just have to think. 3 to the what power will give you 1/3?
Negative 1.
-1. 3 to the what power will give you 3? 1. So there's your answers, -1 and 1. So anytime you see an equation like this, you know it's going to lead to a quadratic equation. You're just going to make a new substitution. Okay, look at your homework tonight. So, come on, the first few, oh, come on. Okay, now number 2. So, number 1, you just have to solve some simple equations. This is just review. Now look at number 2. You guys remember doing problems like that last year? Factoring with negative and fractional exponents. Now the reason why that's so important, because next year in calculus, this is what's going to happen. You're going to be given a function that looks like this. Shall we put cube root of, give me something. Give me a linear thing. 5x.
5.
Plus 3.
Plus
Plus-
5. Plus 5.
No, what? Let's be creative here.
6.
Okay, 6 there. That's not really that creative, but that's okay. Okay, so next year what's going to happen, you're going to apply this calculus rule. It's called the product rule. Right now you don't know what I'm doing, okay? Times 1/3 plus times 1/3 times 5. Okay, you have no idea what it did. I just used the calculus rule. You don't need to know. Okay? Factor it. That you can do. That's an algebra 2 concept. How do you factor something that looks like this?
5x plus 6.
Okay, first of all, what can you factor out?
5x.
5x plus 6 to the -2/3.
Wait.
Oh boy. You can also factor out an x, because there's an x here and an x squared, right? That's the only one I could figure this part. And then if you have a fraction, you always factor out the least common denominator, so you should also factor out a 1/3.
Can you explain?
Okay, let's go back to algebra 1. Suppose you had something that looked like this. 2/3 x cubed plus 3/4 x squared. Okay, how do we learn how to factor this in algebra 1?
X squared.
Okay, first of all, you have an x cubed and an x squared. What can I factor out? Why x squared? How come I can't factor out an x cubed?
Because there's not enough x.
Because 2 is smaller than 3, right? Same thing over here. If you see 5x plus 3 to the 1/3 and 5x plus 6 to the -2/3, what's smaller? Yeah, that's why you factor out that 5x plus 6 to the -2/3, because -2/3 is smaller than 1/3.
Then what's left for the?
Yeah. Okay, let's just do this algebra 1 before we get go to algebra 2. But whenever you have a fraction, you should also factor out the least common denominator. So what's the least common denominator of 3 and 4? Yeah, so you should also factor out a 1/12.
Can you just multiply those?
Okay, now, what's left?
8.
8x plus 9. See? If you factor out what you're supposed to, then in the parentheses will all be integers. Some of you are still going, whoa, what are you going to do there? What? Factoring, people, is just the reverse of the distributive property. If I multiply this times this, shouldn't you get that? And then if I multiply this times this, shouldn't you get that? And do you? Yeah. Factoring is the reverse of the distributive property. How come every year we have problems with this? It's not funny. Okay, so now I factored this out. Okay, now what's left?
2.
Okay, first of all, I factored out a 1/3 from a 2.
1/6.
No,
Negative
okay.
1/6.
No, look.
6/3.
No, 6. You should be asking yourself, 1/3 times what will give you 2? Answer 6. 1/6? What? Okay, we already factored out the x. Okay, now we got 5x plus 6. Okay, this times this.
-3.
Gotta give that. So what power?
-3.
5x plus 6 to the?
-1.
3.
Negative half.
1.
Negative half.
No, 1.
Wait,
No.
I got
One.
1, 2.
That's not right, I'm telling you, it's 1.
Well, we have to say 3. So 1.
It's 1. This is it. That's what's left. Because look, when you multiply this times this, which is 1, what do you do with the exponents? You add the exponents. -2/3 plus 1 is 1/3. algebra 1, people. Okay, plus, okay, I already factored out the 1/3 there, so there's a 5 left.
1.
And then I factored out an x from the x squared, so what's going to be left? X. And then that's, yeah, of course, that's the whole thing, that's why it's a 1. And so there you go. So if you factor out what you're supposed to factor out, then in the brackets will just be
Wait, where's the 5 go? On the far right.
that 5 right there. Do we have to go back to
Oh,
algebra?
no, I get it.
So this times this will give you that. This times this will give you that. I can't believe we're spending so much time on this. And some of us still foggy. What just happened? Then of course you simplify what's in the bracket. So if you distribute the 6, you're going to get 30x plus 36 plus 5x. So your final answer is going to be 1/3 x times 5x plus 6 to the negative 2/3 times 35x plus 36. That's your final answer. I'm telling you right now, this is going to be on the first quiz and the test. There's going to be one problem like this. That's why you better practice on tonight's one. Not just go, oh, I don't know how to do it, I'm going to write it on the board tomorrow.
When's the quiz?
Well, what is today? Well, how many worksheets are there? There's only 5 worksheets, right? So the test next Friday already, right? Okay, then take it Thursday.
I'm not going to hear next Thursday.
Then take it Wednesday. You work ahead. This is not like something that's exotic or even erotic. This is review. This is review. Why would it be erotic, Morris? Okay, did you guys catch on, or do we need another example?
I got it.
Okay, if you need another example, how about look at the examples that I spent the whole summer making? Look at the second page of the notes. Where do I see this factoring with fractional x? Oh, number 2. Example 2. And then look, number 1 is the u substitution that I just showed you. It's all right there if you guys just look. Okay, what else you got to know in tonight's homework? Okay, exponential growth and decay. Okay, now if you see a problem, let's say, okay, a population increases 6% every, give me something, 5 hours. So it's like a population of bacteria, okay? In a petri dish. It's increasing 6% every 5 hours. Okay, how do I model that as an exponential function? What did we learn last year?
0.06
Y equal
x
y naught
times 0.06
P.
1.06
times 5.
to the t over 5 power.
Wait, where's the x? Oh,
Where's
t's
t?
there.
T is an independent variable now because it's tied.
So how come there's 2 y's?
So just half
So I have
P.
a y.
It's the Y initial.
It's y naught. Okay, how many of you took chemistry or are taking it now? Then why isn't everybody raising their hands?
No, because you took it.
The latest you can take chemistry is 11th grade. You can't take it later than that at ELI. Anyway, this is, when this number is bigger than 1, that's exponential growth, right? When this number is a fraction between 0 and 1, then we got exponential
Oh, you
decay.
put the.
Come on, this, Mrs. Fuchs, right?
Yeah.
Tomiyasu.
Oh,
Takazawa.
You know
I like
about this.
I'm trying to think about chemistry teachers. Takazawa.
Sahel.
Tunhill. The 4 T's.
Church.
Tomizawa.
Church.
No.
No, no,
Takezawa.
Food.
I'm trying to remember the 4 T's. Just quiet. Tomiyasu, Takazawa, Tuthill, and Fuji. The 4 T's. That's how you remember the chemistry teachers. Just T.
Is it Lawrence teaching this? She's teaching chemistry,
Barnes.
right?
Yeah,
Why
Barnes.
is she teaching
Oh, the 5 T's then. Let me do it again. Tomiyasu, Takazawa, Tuthill, Fuji, and what did we say?
Barnes.
Barnes. The 5 T's. That's why it's easy to remember. Does everybody see how this works?
Yes.
Does everybody understand what y naught is?
Yes.
That's your initial population, how much you have in the very beginning. Do you guys know why, or did you guys just memorize it?
No, we know why.
Why? Okay, why, Callahan?
Because you have to know how much you're increasing 6% at the end.
Morrissey.
That's right.
That's
Come
not
on.
right, because it's not
That's right.
listening. Jane? No?
Because it's given.
Because if it's before the 5, then that would be.
No. Why is why not your initial amount?
That's right.
Because not means.
No, I said why.
Because
Oh,
not.
why? Because you have to know what you're increasing.
No, but Mr.
Like,
Point,
no.
if the T would be
Oh,
0.
Morris
Wait, wait,
said-
what, Morris?
If the T would be 0, then now we won.
Okay, that's too late already.
It's stuff.
Because not looks like a 0, so it's
No,
like.
the T would be 0. The T would be 0. So
Okay, very
the T would
good.
be 1.
Okay,
So
love
the
that.
initial population would be 1 times the population.
Love got it.
Wait, why?
He said initial means when T is 0.
That's what I'm getting to. This is what it is.
Why did you say that? So what happens when you plug in 0 for T? What is any number to the 0 power? 1. So what is 1 times this?
The same thing.
No, this. That's why this is how much you have at the beginning. You guys probably just try to memorize it. Now, if a population increases 6%, do you see why that's 1.06? Because a lot of you are saying, how come it's not 0.06? Because how do you increase something by 6%? Something plus 6% of that, and of course, doesn't that simplify to 1.06x? That's why it's 1.06. And if it increases every 5 hours, do you see why it's T over 5?
Yes.
Because then when you plug in 5, then you get 5 over 5, which is 1, and then this to the 1th power is that.
But if you had 1 hour, wouldn't it be
What?
No.
to be 1/5? So it'd be the cube, the 5th root of. Oh, but it has to be.
It's still gonna be bigger than
Oh,
1,
yeah.
right? Okay, now what if we have something that decays? Like, can you think of something that decays? The price of your car.
Banana.
The price of a banana. I guess that one. Okay, let's say the price of a banana.
What because it gets mushy?
Okay, I'd rather use a car. I feel safer with a car. Depreciates. Give me a percent. 20% every.
5 years.
No.
10, 5
Every.
months.
Okay, 5 months. Every 5 months. That's good. But I don't think it. I mean, that's not really that true. But that's good. Let's just use it. So how do we write an exponential function that models this? Y equal y naught. What number do I put in? 0.8.
T over.
Because it's x minus 0.2x, right?
12 T over 5.
T over 5. T over 5.
What is? You say 12.
Yeah, 12. What? Yeah, 12 T over 5.
No, we're working in months. Since you said months, just like this one, we're working in hours, right?
Wait.
Of course, if you change the units, then just do dimensional analysis, right? You guys know how to do that, right? Okay, so tonight's homework is super easy. It's like ridiculous. Unless you're ridiculous, then it's gonna be super hard.
Can we use a calculator?
Yeah, no. It'll tell you when you can use your graphing calculator. Like number 6, you have to do exponential regression. Do you guys know how to do linear regression?
Yeah.
Then we did quadratic regression. Then we did cubic regression. Now we got exponential regression.
When do we do?
And then when we study trig, you can have trig regression.
That's the thing where you had that R thing, right?
And then when we study log, we have
What
logarithmic
is regression?
Best fit curve. Best fit
Why do
curve. Okay, now why do we study exponential and logarithmic functions? Is there like uses of it in real life?
No.
Inflation.
Yeah, right here. Well, I just showed you, right? Exponential growth, exponential decay. What about interest? Did you
Oh,
guys
wait,
hear
did we do
learn PERT last year?
Simple.
Remember PERT?
Yeah.
Yeah, PERT. P.
What?
I told you.
But PERT P is the same thing as why not though.
Yeah, that's what I was saying, and I was like.
Why are you telling him? Tell me.
I was saying P. Why?
That's the shit. Okay, but what about music? Does anybody know why exponential functions are used in music? Okay, so here, let's look at one octave on a keyboard. 1, 2, 3, 4, 5, 6, 7. Okay, so the black keys are too long, man. Anyway, this is middle C. This is middle. You guys know what middle C is? Now, you guys, if you guys are in orchestra and band, then you know that the A above middle C here has a frequency of 440 hertz, right?
How do you know that?
The tuning fork.
metronome?
Who uses those?
One metronome?
Don't you guys ever heard of a tuning fork? This metal fork? Go-
Physics.
That's to tune your
Who
instruments.
still uses those?
Don't they have like electronic tuners?
Okay, whatever. Okay. Cut A above middle C is 440 hertz. Now, do you guys remember Donald Duck in Mathemagic Land?
Yeah.
Remember how they talked about Pythagoras knew about the music?
Yeah, the strings, right?
Yeah, remember had the string?
And then he divided it in
And
half.
then, yeah, so, ding, and then it, ding. Wait, I can't do it. Ding, ding, ding. Every time you half it, you get an octave higher, right?
Yeah.
Okay. Now, didn't they say they made a mistake in Donald Duck in Mathemagic Plan? They said you can use
Oh,
that.
the pie. Yeah.
No, not the pie. I'm talking about the music thing. They said that this thing that he talked about, remember, the ratio of the things is 2 to 3 to 4. It forms a nice chord. Yeah, and that's what Pythagoras discovered. If you go 2 to 3 to 4, see, since this is twice that, this is going to be an octave, and this is going to be the fifth, right? Because it sounds. You guys know what a fifth is? Da, da. That's a fifth. Yeah, so. Da, da, da. No. Anyway, and then they said that that's how we got our scale today, but that's wrong. Because if we use Pythagoras' system, then there's inconsistencies in it. So that's why I think around in the 1600s, they developed the even-tempered scale. You guys ever heard of that? And that's how we tune the instruments today. We don't use this. Okay, so if you have A, 440 hertz, if you go exactly one octave above that, okay, let's draw another octave. 1, 2, 3, 4, 5, 6, 7. Wait, I did too many, huh? It's too many, fool! So this is C, so C sharp, so if I go one octave above A, shouldn't that be 880 hertz? See, but the thing is, Pythagoras didn't know anything about frequencies. All he knew about is length of string, and then you half it, and then you get an octave higher.
How do you know what an octave was?
Well, maybe they didn't call it an octave, but then maybe they called it something else. But you know what I mean? It's like the same sound but higher. You know what I'm talking about? So yeah, it works. And then what about here? So da. What's a fifth above A? You guys know what a fifth is? Da, da, E. So using Pythagoras' system, remember the ratio is 2 to 3 to 4, right? That forms a nice chord. What would be the frequency of E then? It would be 660 hertz. Da, da, da. No, the ratio is 2 to 3 to 4.
But it's happening between them.
Okay, but that's not how we tune now. Okay, now we use the even-tempered scale, which is this. It's 2, the frequency is 440 times 2 to the x over 12 power. It's an exponential function. What do we call this y again? Where this will give you, x is the number of half steps above the A above middle C. So if you're at the A above middle C, you're not any half steps above it or below it. So if you plug in 0 for x, what do you get? You get 2 to the 0 is 1 times 440, you get 440. Okay? But if you want to get the frequency for E above the A above middle C, then how many half steps do you have to go? 1, 2, 3, 4, 5, 6, 7. So if you want the frequency of E, you would have to plug in 7 for x. So the frequency of this E would be 440 times 2 to the 7/12th power. Okay, who's got a calculator? Okay, Kobe got it. Punch it in. It's going to be kind of close to 660, but it's not exactly 660. Because we don't use Pythagoras' system anymore.
It's 659.2.
659.2. See? It's not quite.
zeroing.
And yes, it
No,
does.
like, can we actually
Because
hear?
if you use Pythagoras' system, you get inconsistencies.
Yeah, but like, can we actually hear the difference between this like 0.8 hertz?
Most people cannot tell. But then when you get to other notes, then you're gonna really hear it. You know what I'm talking about? There's inconsistencies. Because every time you go a major fifth up, it's gonna multiply the frequency by 1.5 if you use Pythagoras' system, right? Okay, here, I'll show you since you guys don't believe me. Okay, look. Okay, what's a major fifth above E? You guys know what a major fifth is? Da, da, that's a major fifth. Isn't that, okay, who plays string instruments? Isn't it go by fifths or does it go by fourths on these strings?
Fourth on the bass.
Huh?
Fourth on the bass, based on all this.
Okay, so you know what fourths and fifths are.
Yeah.
Okay, what's a major fifth above E? B, it's B over here. Okay, so we start with A, E, okay. So multiply this by 1.5. Calculator. Come on, we don't need it. So this is 440, this is 660, and then the B
990.
990. Okay, what's a major fifth above that? No, F sharp, F sharp.
1480.
So what's that times 1.5? Quick.
1354.
39.
What? I can't see.
Just take half of it and add it.
1480.
What's half of this?
45.
440.
445, so add 445 to it.
1485.
Okay, well, how about you take out a calculator and multiply it by 1.5?
14.
How can it be 14?
13.
35.
1485.
Take your calculator. This is period 6. We're supposed to get a smart time.
1.5?
Yeah.
1485. It's not 440.
Wait, that's not 45. Kobe is right. So what is it?
1485.
1485. Yeah, it's not 4. Okay, anyway, so what's a major fifth above F sharp? Okay, it's C sharp. Okay, so multiply that by 1.5. And keep all the decimal places if there are any. What is it?
2,227.
2,000.
227.
Wait, English now. 2,000.
200.
2275.5.
No,
Let's do it in the beginning.
2.
There's another.
227.5.
I gotta have 4 digits here.
222.
Oh, 2227.
0.5.
Okay, keep that. Okay, what's a major fifth above that? G sharp. Okay, go. Multiply that by 1.5.
3,000. 3,300.
Just give me digits. Forget this thousand digits. 3.
341.25.
Say that again.
3341.25.
Okay, what's a major fifth above this? G sharp.
T-shirt.
D sharp. Okay, multiply that by 1.5. Go.
5011.875.
5011.875. Okay, major fifth above D sharp
A sharp.
would be A sharp. Go. Multiply that by 1.5.
7517.8125.
7517.8125. Okay, A sharp is the same thing, so it's going to be F then, right?
Yes.
Yes. Come on. Okay, multiply that by 1.5.
11276.71875.
71.
875.
Oh. And then major fifth above F is C, right?
Yeah.
Okay, go.
16915.
16915.
915. .07813.
I think we went too far. You know, we should have just done this. We should have just done this. Pythagoras said that if the ratio is 5 to 4, then that gives you the major third. You know what a major third is? Da. Okay, when you make a major chord, here, for example, da, 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 da. I don't even know if I'm starting at C. Da, 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 da. So from here to the fifth, that's going to be, the ratio is going to be 2 to 3, right? But if you go da, da, the major third is going to be 4 to 5. That's what Pythagoras said. So, if you start at A, what's a major third above that? What's the major third above A? It's C sharp there. What would be the frequency of C sharp? The ratio is 5 to 4, so multiply this by 1.25. Okay, multiply this by 1.25. What is it? 550 exactly? Okay, but look over here. If we start here at 440, we go over here, 660, 990, 1475. We get to a C sharp up here, which is 2227.5, and here's a C sharp here. If I double this, what do you get? Double that. 1100, double it again. 2220. See how it's off? See, that's why Pythagoras' system doesn't work, because you get inconsistencies like that. But if you use the even-tempered scale here, this works. Because every time you go an octave above, which is what? 12 half steps, can you see? The thing is going to double. So that's why this is the one we use today. Pythagoras' one doesn't really work, but it does sound good when you just do the 1, 5, and the 8, 1, 5, 8, on 1, 5, 8. But otherwise, yeah, you get inconsistencies all over the place.
I mean, like 7.5 is like 0.1%.
Yeah, but does anybody in this room have perfect pitch? No, because you can press a note, they can tell you exactly what it is. And they can tell, oh yeah, it's almost a B flat, but your piano's a little flat, so then you're going to call a guy to come and fix it.
Just keep that.
Yes.
Give that too.
Why don't you just change that once?
Because you can't.
You can just hear it. I had a friend, a classmate at Castle High School. She had perfect pitch, and then I don't know. She said the way she could just hear it in her skull, the way it resonates in her skull or something. So she's a piano teacher at Woodall. No, we're not ready yet. Anyway, this is one of the examples of exponential functions. We can use it for. Yeah, we have plenty of time. How long did that take? Just talking about that. Okay. Anyway, since we never did talk about the golden ratio, we're going to do it today. No, we didn't. Anyway, Donald Duck in Mathemagic Land, didn't they talk about it a lot? Comes up in Greek architecture and art, right? And I already told you, right? The golden ratio. What is a golden rectangle?
When you cut it into a square, and you put
A golden rectangle is the most perfect rectangle the Greeks thought there was. Now, to get a golden rectangle, what you do is you portion off a square here. If this leftover rectangle is similar to the original rectangle, then that's a golden rectangle. Yeah. Yeah. Okay, so what is the ratio of the length to the width in a golden rectangle? Yeah, you already know it's the golden ratio, right? Which is phi, which is 1 plus v5 over 2, right?
Yeah.
Yeah, but do you guys know how to get that? How do you actually derive that? Well, why don't we call the width x, okay? So this is x, because this is a square. And then what? What is this right here?
Why?
Okay, you know what? Okay. Why do you want to? Okay, you want to call it y? We call it y. Okay, so this is y. So what is the ratio of the length to the width in the original rectangle?
X
X plus y over x. And then in this rectangle, since it's similar, what's the ratio of the length to the width? X over y. And then they should be equal because they're similar, right? So
Wait. Don't you have to put y over x? Because the.
no, we're going length to width.
Yeah,
Length
yeah,
over
yeah. Y is
length over width is equal to length over width.
Oh, because it's longer that way.
I just figured out a better way to do this problem, but you want to do it? Let's get that. Okay, so cross multiply, so you get xy plus y squared is equal to x squared. Now what are we trying to find? We're trying to find the ratio of x to y, right? The length to the width. So this is a math team trick, okay? If you want to find the ratio of x to y, you know what you do? Boy, this is the secret. We just did this last meet. But you're there, but you should know it anyway. You know. I'll just tell you. You let y equal to 1. This is a trick you can use on any test. If you want to find the ratio of x to y, just let y equal to 1. Because then what do you have to solve for then? X. Because x will be the ratio of x to y, since y is 1. So just let y equal to 1, and what do you get? X plus 1 equal x squared. So make one side 0, x squared minus x minus 1, and if you recognize that equation, that leads to the golden ratio, right? So here, you don't believe me here, use the quadratic formula. Plus or minus the square root of 5 over 2. See, I told you. No, you should just remember this equation because it comes up a lot in mathematics.
But we have to get
Wait,
rid
you
of
don't
it.
need the minus.
Because how can it be negative?
Yeah, okay, I got it, sorry.
Anyway, so that's what the rate. And didn't I tell you about like it comes up in nature, right? On humans, if you take this length divided by this length, golden ratio.
So weird.
This divided by this, the distance from here to here divided by the distance from here to here, golden ratio.
That's sick. Are you
And that's why in nature, we talked about this, remember the banana thing I told you?
You split in 3.
Yeah, so in nature, lots of things come in Fibonacci numbers, right? I think I showed you guys this.
That's the thing with the sunflower.
Wait, what does Fibonacci have to do with golden ratio?
I think I showed you this, but you guys don't remember.
Lucifer, is that the thing with the sunflower too?
Yeah,
Yeah.
so that's why in nature, a lot of things are going to be Fibonacci numbers.
That's why 4 is.
That's why a 4-leaf clover is rare, because clovers usually have 3 or 5 leaves, that's why.
But what does the Fibonacci have to do with the golden ratio?
Okay,
Can you just put?
I'll show you again. What happens when you take each number of the Fibonacci sequence and you divide it by the previous one? What's 1 divided by 1? 2 divided by 1? 3 divided by 2? 5 divided by 3? 8 divided by 5? 13 divided by 8? If you look at these numbers are getting closer and closer.
The thing over there.
Oh yeah, closer to the golden ratio.
Oh! What?
How is 13 over 8 equal to 8 over 5? Wait,
No.
one's repeating and one's...
Anyway, these numbers are getting closer and closer to something, and you know what that is?
Golden.
The golden ratio, because the golden ratio is 1.618 approximately. And that's what the Fibonacci sequence has to do with the golden ratio.
You know, it's pretty cool.
What?
Every 5 terms there's a 5. I just figured that out. I'm not even joking.
Could you add
Try it.
terms for it?
Oh.
21, 34, 55.
Oh! Okay, wait. And you see something else cool? Go. Okay, put 1 and 1 together, you get 11. Okay? Just put them next to each other. And then put 2 and 3 together. No, sorry, 1 and 2 together. So you get 11, and then you get 12, and you get 23, you get 35, and you get 58. It's another golden ratio. And you get 93. No, yeah, dude, I figured this out when I was like 8 years old.
Okay, Trey, do it again. I'm not understanding what to do.
Do 11,
11,
plus, and then comma 12.
comma 12.
Yeah, and then comma 23, then comma 35, then comma 58, then comma 93, and then comma 151, and then 244. Keep going.
So where do you get all these numbers from?
And what are these
You
numbers?
just put them together. So you 1 and 1, and 1 and 2, 2 and 2.
So what's the...
What? Say that again?
Go. 1 and 1, 1 and 2. And then you gotta add those two. And you add the middle ones.
Where do you get the 93? So what are those numbers?
It's just like the same thing as
It's a Fibonacci-like sequence, right? You start with 2 terms and you just add these 2 to get the next one, right?
yeah, I guess.
Oh, I get it. Wait, that's cool. I know.
Okay.
That's it.
Anyway, the golden ratio comes up a lot. So I'm trying to figure out what?
I don't get where you get the 93 from.
Because you add 8 and 1, you get 9. Add the 8, put it 3 on.
the middle one.
Yeah, you add the ones between the, you like, if it's
Oh, I
0,
get
8.
it. Okay. The two. Okay.
That's like the secret to life right there.
No, that's 42.
So you solved this when you were like...
It's just like playing around.
Okay, now I can pass out the test. Okay, the average was 85. Here it is on the board. That's the whole test. I think this is the first time every single person took it on time.